Curvilinear motion is defined as motion that occurs when a particle travels along a curved path. The curved path can be in 2 dimensions in a plane or in 3 dimensions. We're going to analyze this type of motion with Cartesian coordinates. Recall particle p moving along a path s of t. Let r sub p slash e be a vector that describes the position of p with respect to point E, where point E is fixed in inertial reference frame E. The position vector of p with respect to E is a function of time such that in Cartesian coordinates it is x of t ex plus y of t ey plus z of t ez. If the velocity of p with respect to E is the derivative of the position vector, then the velocity of p with respect to E is x dot ex plus y dot ey plus z dot ez, where anything with a dot over it is by definition the derivative of that variable with respect to time. Recall that we often write x, y, and z without the t in parentheses, even though they're frequently functions of time. We can also write the velocity vector as vx ex plus vy ey plus vz ez, where vx equals x dot, and so on. Again, vx, vy, and vz are still functions of time, even though we haven't written the t after them. To recap, vx, x dot, and dx dt are just 3 different ways to express the same quantity. And remember, the velocity vector is always tangent to the path of motion. Now we're going to do the same thing with acceleration. The acceleration of p with respect to E is the derivative of the velocity vector, which is equal to the second derivative of the position vector. And this is x double dot ex plus y double dot ey plus z double dot ez, where anything with a double dot over it indicates the second derivative of that variable with respect to time. We can also write the acceleration vector as ax ex plus ay ey plus az ez. Again, ax, x double dot, and dx squared dt squared are all just different ways to write the same thing. Also, the acceleration vector is generally not tangent to the path of motion. Let's do an example. Here we're given acceleration of a particle p as a function of time. We have the initial position at the origin and a value for the initial velocity. We need to find the position and velocity vectors when t is 4 seconds. I will add a picture for this problem, though working in 3 dimensions makes it difficult to visualize the motion. We will start by finding the velocity vector. Since we have an expression for acceleration as a function of time and we need velocity, kinematic equation 2 is the best choice. We have to rearrange this equation in order to integrate, and when we do integrate, we set the lower limit of velocity to be the initial condition of 5 meters per second in the EY direction. The initial condition for time is just 0. Then substitute the expression for acceleration that was given. Then take the integral. Then rearrange. Note that this is the expression for velocity as a function of time. I'm going to ask you to remember this expression. We will need it again later. For now, substitute t equals 4 seconds into the expression, and we find that the velocity vector is negative 1.6 ex plus 13 ey plus 20 ez in meters per second. If you're ever asked to find the magnitude of the vector, you just take the square root of the sum of the squares of the magnitude in each direction. We still need to find the position at t equals 4 seconds. Using kinematic equation 1, we know that v equals dr dt. Rearrange to separate the differential terms. Then integrate, noting that the initial position is at the origin, so the initial position is the 0 vector. Now we need to substitute an expression for the velocity of p with respect to E. It is very important that we use the function of time that we found for velocity in the last step. Using the final value of velocity at t equals 4 seconds will give us the wrong answer. Now we can integrate and evaluate. Plug in the value t equals 4 seconds and we find a value for the position vector. The last problem involved multiple dimensions, ex, ey, and ez. but the solution required only differentiation, so we worked with all directions simultaneously. In many cases, however, the problem will be more complicated. In these more complicated cases, it is often helpful to work in each dimension separately. We can do this because we define mutually orthogonal or perpendicular axes. The orthogonality ensures that the motion along each axis is independent of the motion in the other directions, and this allows us to work in each direction separately. Here is a very simple example. If we have a position vector equal to x ex plus y ey, where x is t squared and y is 3x to the 1/2 power, and we want to find the velocity vector, then we can compute the components of velocity in each direction separately and then reassemble them at the end. We know that velocity is the time derivative of the position vector, and we write it as dx dt ex plus dy dt ey, which is the same as vx ex plus vy ey. Let's make a note that we're working only in the ex direction first. Vx equals dx dt, which is the time derivative of t squared as given in the problem statement, and Vx turns out to be 2t. Then in the EY direction, Vy equals dy dt, which is the time derivative of 3x to the 1/2 power. Again, this was given in the problem statement. We can substitute x equals t squared, so we have the derivative of 3t with respect to time. So Vy is 3. Reconstructing the velocity vector, we have 2t ex plus 3 ey. Let's do a more complicated example. A balloon, B, travels from point E to its current location along the path shown. Note that the dashed line is the path of motion, not the string. If Vx equals 2t feet per second, find the acceleration, velocity, and position vectors after 10 seconds. Let's start by writing down what we know. We know that the position of B with respect to E is x ex plus y ey, where y is 1/10 x to the 3/2, as shown in the picture. This is not all that helpful. We can't integrate with respect to time using this information. The only other thing we know is the expression for velocity in the x direction. This is 2t feet per second. We also know that we can work in the ex direction by itself. If we do, then dr dt from equation 1 becomes simply dx dt. If we rearrange that expression, we get dx equals vx dt. Substituting that expression given for Vx in the problem statement, we get dx equals 2t feet per second dt. This is really helpful because now we can integrate. When we do, we see that x equals t squared feet, and if we substitute t squared back into the original position vector expression for x, we get t squared ex plus 1/10 t cubed ey in units of feet. This is the final expression for the position vector as a function of time. We will need this again to find the velocity vector, but if right now we plug in t equals 10 seconds, we find that the position of B with respect to E is 100 ex plus 100 ey in feet. To find the velocity vector, we need to take the time derivative of the position vector. Remember to use the function of time and not the value of the position vector after 10 seconds. Plugging in t equals 10 seconds, we find that the velocity vector is 20 ex plus 30 ey in feet per second. Taking the time derivative of the velocity expression, not the final value, gives us acceleration. At t equals 10 seconds, acceleration is 2 ex plus 6 ey in feet per second squared.